thank you for being here. I'm quite happy to be back in Santiago. It's a really nice place to have a city. As Alan just said, I'm a PhD student in UCLouvain, where the last CT happened. And my advisors are Tim van der Linden and Xavi Garcia Martinez, which explains why I spent some time here. So if you have any questions about the place, you can always ask me. Today, I would like to talk about this work with UCLouvain and Tim van der Linden. The first 10 minutes, I will try to explain how we got to that question, and then I will try to explain to you the categorical tools I will be using for this result. Okay, so let me start with just being sure that we agree on some notation, or at least some words. K today will be a field, and I consider its characteristic to be 0. You can ask me at the end what happens if you change that, but I think for the simplicity of this talk, I will keep it like this. K algebra means a vector space with a multiplication on it. And what I insist on today is that this multiplication on this vector space, I know nothing about it. I just know that it is bilinear. You can distribute over the addition. That's why we call it multiplication. But I don't know if there is a unit, if it is associative or it is commutative. I just that's why we call it non-associative algebras. This does not mean that they are not associative. It just means that not necessarily I assume anything on it. Okay, and the last word we should agree on, because I will use it a lot, is a variety. For me, a variety, I think about a variety of K algebras, and this means a collection of K algebras, the collection of all K algebras, I should say, of all K algebras which satisfy a chosen set of equations. Okay, so main examples I have in mind and I will mention today. The first one is the variety of Lie algebras. This one is defined by two equations. The first one is anti-commutativity, and the second one is the Jacobi identity. Okay, that's the variety of the algebras. I will mention also the abelian variety, which is determined by the equation x times y equals 0. So you might say, I was not expecting that for the word abelian. The reason is that those variety, I look at them as categories, and this is the only variety which is abelian. So that's why I call it abelian variety, because it's an abelian category. The last two I will mention today is the variety of associative algebras, which you can guess is this one. And then I will also use the same one but with a C in the front. C stands for commutative. So those ones are associative algebras, and this one is commutative and associative algebras. Okay, now we are ready to mention the first result. This one was done by Xavi and Tim before I was their PhD student. Let V be a variety if V is LAC. So LAC means locally algebraic active and closed. It is pure categorical condition. It was introduced by James Gray, I think in his PhD thesis. I will not go in this direction and I will not explain what is this, but what you have to keep in mind is that it is categorical. If V is LAC, then V is either the variety of the algebras or V is the abelian one. Okay, so I like this result. Why? Because this is category theory, but those are algebra. This is equational. So you have a link between categorical conditions and equations. And also it means that this LAC condition is so strong that you do not have magic numbers. The first project I wrote as a PhD student, Xavi and Tim were wondering for another condition here, which is called action representability. This was introduced by Corentin Vienne and Kelly, and it's also a categorical condition. And at the time, the conjecture was that if we replace LAC by action representability, then we get the same result. And that was the first project we worked on together. And actually, one of the key parts of the proof was proven here to Flo's perspective. So this was the second result. And also, again, I insist, this is completely categorical, that's why I like this way. So the question we tried to understand with Ulo and Tim was, what if I want here the variety of associative algebras? Which condition should I put here to find it? That was the first question, and actually we did not answer this question. We put here a categorical condition, which we call Cosmash associative. But we did not find associative, we find commutative and associative algebras. So again, I think it's quite nice to have this completely categorical notion related to the equational condition. So now you have the motivation. I only need to explain to you what Cosmash associative means. That's the second part of the talk. Usually, when I think about some categories, I have in mind semi-abelian categories, which were cited today a lot, I think. But if you don't know them, it's fine. What I will explain now, if C is pointed and finitely complete and co-complete, it's okay. Okay. So let's take two objects, X and Y, in a category C. I need to define the binary Cosmash product, but first we'll consider the following map. This map, since my category is pointed and complete and finitely co-complete, is a canonical map. It's the one going from the co-product of X and Y to the product of X and Y, and some people like to write it in the matrix way. I like it too. And the definition of a binary Cosmash product which I write with a diamond like this. This object in the category C is the kernel of that map. This was first introduced by Mantovani and Metere, but the name comes from a dual notion from Carboni and Giannelizze. They defined the smash product because it is dual because it is just the co-kernel of this map, and the reason it has the name smash product comes from topology. I wanted to say, in semi-abelian categories, this map is a strong AP. So looking at the co-kernel is not really interesting. Okay, so what I want you to have in mind is that this binary Cosmash product goes in the direction of commutator theory. Why? Because if we look at the category of groups, people living here, actually people generating the Cosmash, they just look like commutator worlds. Like this. Okay, but you have to keep in mind that this Cosmash lives in the co-product. So those, you have to look at them as worlds, not as elements of a larger object. So if you want a sub-object, a commutator sub-object, then you would have to take a regular image, and this is called the Higgins commutator. It is also defined by Mantovani and Metten. Okay, now, the question I would like to answer is the following. If I give now 3 objects in the category C, do I have a way of defining a ternary Cosmash? Like a ternary commutator, but about 3 objects. The first idea would be, well, you just defined the binary Cosmash, so why don't we repeat the binary Cosmash? I first do the Cosmash with x and y, and then I do the Cosmash with z. The problem of this idea is the following, is that you made a choice here with the parentheses. If now I define it in this way, the problem I have is that those 2 objects, they are not isomorphic in general. You can have a counterexample in the variety of Lie algebras. So now you would say, but that will be your definition of Cosmash associative. Those 2 objects are isomorphic. The problem is that you do not have a canonical map here. So I don't have a way to compare them. I need to compare them. What is true is that in the Cosmash associative category, those 2 will be isomorphic, but it's not a good starting point. So what's the good way of defining the ternary Cosmash? Well, again, I take a canonical map, and it can also be written in a matrix way. And it goes to the co-product of x, y, and z to the co-product of x and y times x and z times y and z. So what it does is that here the first component is you just make everybody living in z vanish, and then you make everybody here in y vanish, etc. And again, as before, to define ternary Cosmash product, you just take the kernel of this. So I should mention that this was already done in the dual case by Carboni and Giannelizze. But here what you can see is that I do not write it with any parentheses. If I have no parentheses, it just means that it is the ternary one. And the ternary Cosmash product, therefore, is the kernel of this one. Okay. What is good with, at least better with this definition, is that now I can compare this object with those. Okay, time is running out, so I will not draw the diagram, but it's not a complicated one. It is just universal properties. But here you have a canonical map from here to here, and you also have a canonical map like this. And now you can easily guess what a Cosmash associative category is for me. It is when those two comparison maps are isomers for any x, y, and z in the category C. Definition. C is Cosmash associative if and only if those two comparison maps are isomers. For any x, y, and z. This definition comes again from Carboni and Janelice, but they called it the smash associativity. In the original definition, they asked that those two maps are isomers, but actually if you ask only one for any x, y, z, it is enough. The reason is that you can easily see that if I move the place of the x, the y, and the z, it does not change. Okay, so now, in some sense, I finished my duty, because you know what a variety is, you know what Cosmash associative means, and then you can understand this result quite easily. I would like to finish by just a few examples and some questions we have in mind with this problem. The first one I should mention, examples of category which are Cosmash associative. Well, of course, commutative and associative algebras because of our result. But what is interesting here to understand is that the reason it works so well is that here the Cosmash is the tensor product. Another example is all abelian categories. And for more semi-abelian categories, it starts to be difficult to find other ones. Groups do not satisfy it. So Cosmash associative in my mind is quite a strong condition. Another one is actually Boolean rings. Yes. By the way, Boolean rings satisfy a lot. I think it's the category I know which satisfies the most conditions. The only one that does not satisfy Boolean rings is black. And some of you know that I have my favorite category always in mind, which is hating semilattices. This does not satisfy Cosmash associativity. I will just finish by saying the following. The first question I have is, well, we did not find a condition for only associative algebras. So what could be there, I don't know. And the second thing we have in mind, actually we are working on this already, is I defined the binary, well, I showed you the definition of the binary Cosmash product. I showed you the ternary Cosmash product. When mathematicians start to count, they never stop. So we should have a definition of the n-ary Cosmash product. There is one. It is defined by Tim van der Linden and Manfred Hartel. Again, it is dual to what Carboni and Janelice did. And one question which arises then is, okay, can we talk about n-ary Cosmash associativity? What happens? Does the lower degree imply the higher degree? And questions like that. That's all for today. Thanks for the attention. Okay. Other questions? Please.
trying to work out the dependency on K. So you say it's Cosmash associative, then V equals C associative K. So
yeah, because K is fixed. The field is fixed.
But then I was thinking for your example of Boolean rings, would that come by a different K, or you just is K part of the structure of V then?
No. So here inside of these are K algebras. K is not inside of it.
Yeah, on the Cosmash associative condition.
Yeah.
That's got no mention of K.
No. Cosmash associative is a categorical condition. It has no link to the K. Am I answering the question?
Well, I'm just confused how the K is derived.
It just means that it is fixed. I do not, once I chose the field, I do not know
it is already algebras over K. So it's given that V is algebras
over
K.
V is
Yes.
already
Yes. I should maybe write
right. Yeah.
the K variety.
I got it.
Thank you for your talk. It was interesting. I'm just curious. In this new work, do factors feel these characteristics in playroom, which is you started saying that K is a characteristic zero.
Yes.
Is this hypothesis, and this is for all the work I know of K and so on. Also in this case, this is the necessary position, and how does it play a role in this?
Yes. So actually, if K is not characteristic zero, what we did in the paper is we proved that if it is an infinite field, then V is a subvariety of commutative and associative algebras. So yeah, asking K to change a little bit does not make the same result. But if you look at the paper, we did not choose this terminology. We chose the terminology of operatic varieties, which means that the identities which define the variety are multilinear. And the multilinearity has a strong role. If I don't have the multilinearity, then what can happen is here I have a sub-variety. But if I have a finite field, then Boolean rings appears because it is a variety over Z2.
Is related to Higgins commutator?
Yes.
So that this means precisely that Higgins commutators of length.
Yes. So the Higgins commutator, the definition is the following. If I take x and y to be subobject of A, I do the coproduct of x and y, the Cosmash product of x and y. I send it to the coproduct, and here then you have a map to A. The definition of Mantovani and Medere is here you take the regular image. So here you have a mono, and that's the Higgins commutator. That's exactly the definition of Higgins commutator, which is not co-commutator. It's not the same.
So because it seems to me that it is somehow related to work I have done with Dominique Bourg.
Yes, it is.
Because somehow it is very close. So if you have a solid category, then you can define different notions of nilpotency. And so somehow, I think that in diamonds you can also define it as a kernel of a map of cubes. And then what I did with Dominic is that we somehow showed that the vanishing of these kernels, so the vanishing of an iterated diamond, corresponds to some notion of k-nilpotency.
Yes.
And so this would just say that it is one nilpotent, so it's a billion.
Yes.
But I'm not. This is very subtle, so I'm not sure whether this is an equivalence.
The main difference with the work you did with Dominique, I think, is that you defined two nilpotent. You had two kinds of nilpotency, And I think here what happens here is that this is a sub-object, and x and y are sub-object at first. So talking about nilpotency only about the Cosmash, not asking x and y to be sub-objects, is another kind of nilpotency. And this I think was done by Tim and Manfred.
This condition is much stronger than asking that the commutates coincide. Taking of the image really collapses both.
And one way of seeing a big difference with the fact that here you are taking object or sub-object is if I ask, for example, a Birkhoff subcategory of a category of groups, and I want it to be Cosmash associative, it's not the same as asking that the commutator is associative. Because the important groups, then the commutator is associative because the commutator vanished. But I'm not sure that the important groups are Cosmash associative. This I don't believe it actually, because this lives in the coproduct, it does not live in the sub-object. So one open question I mentioned once at one another was, is there an only Birkhoff subcategory of the category of groups, which is Cosmash associative? Is there a category of abelian groups? It's possible, but I don't know. But if you do it on computators, then the answer is you have the important groups.
Is the result here that you have there, the term that Xavi and this computer one, is this also computer-based?
Yeah. Okay. It was less scary this time, because at least, well, we had Ulo who is able to code this, and also we already did it twice. Xavi and Tim for the lag part, then with myself for the action representable part, and then with this project we also had to compute a lot of polynomials and to see that there is some kind of incoherence at some point. So it's quite familiar, but I like this.
Other questions or comments?
That definition, it's a naive question. Is it equivalent to just isomorphism between those? So that arousals isn't that the same as, can we prove that it is the same that there is an iso between them?
Ah, you mean there exists one between this and this?
Yes.
The problem is that, yeah, I cannot build a canonical map and then ask it is an iso. Like if you draw the diagram to find this map, okay, you see something commute and then you use the fact that this is a kernel, this is a kernel. But
maybe it's just equivalent to.
Oh, yeah. For me, the problem is the existence. I don't.
Well, if there are arousals, it exists.
Yes.
If it exists, then.
Yeah. Ah, okay, like it.
But even if that iso exists, it doesn't tell you anything about the term.
Yeah, what I would not be surprised is that it can happen that these two are isos and this is mono. But okay, maybe I'm saying something I don't know. So it's a good question.
Is it easy to see that the Boolean rings are Cosmash associative? Give a reason why they are.
Yes, the reason is that is this. It takes a bit of work, but in the paper it's not that long. It's more algebra than category theory. So in the paper actually we did not put the details because you just mimic the technique for that. You have to check that at some point a coproduct is well behaved and then it's fine.
Okay. If there are no more questions, then let's thank